This chart has a summary of comparisons of the measures of center and spread, the median versus the mean, the IQR versus the standard deviation. We're actually going to talk more about the IQR and the standard deviation in a later video. So this video is mainly comparing the median and the mean. I'm not going to read through the chart because most of everything that we're talking about in the chart is going to be illustrated by some of the examples I use. So first example, what do the mean and median measure? The median balances counts, whereas the mean balances deviations. To illustrate this, I have a very small data set of the points 1, 2, 3, 6, and 8. If we look at the median, which is the middle number of the data, notice that there are two data values to the left of the median and to the right of the median, and two data values to the left of the median, so it balances the actual number of data values. Whereas the mean balances deviations. I've calculated the mean here, which is 4. So here's the mean. Now notice what the mean balances. We have a deviation in the positive direction of 2 and another deviation in the positive direction of 4. 6 is 2 greater than 4 and 8 is 4 greater than 4. In the negative direction, then we have a deviation of -1, of -2, and of -3. So notice that if we were to add up all of the deviations, I probably should have left myself a little more room to do that, but -3 plus -2 plus -1 plus 2 plus 4 ends up equaling 0. So the total amount of positive deviation from the mean and negative deviation from the mean always adds up to 0. So that's what it means by the mean balances the deviations. Another characteristic of the mean and the median is that the median is resistant to outliers. In other words, if I change this point from 8 to 18, the median didn't change. However, the mean will. So if I look at recalculating the mean now moves from 4, now it's 6 instead of 4. So it is called sensitive to outliers. Now just because the median is resistant to outliers doesn't mean that it doesn't change at all. It means that it changes either none or very little. So let me give you an example here with a little applet online. So I can put some data values on here. So let me just kind of scatter some data about. Okay, so we have a fairly symmetric distribution here, and the mean are pretty much the same. Now notice if I add a couple of outliers here, notice that the median is staying the same, but the mean is moving towards the outliers. So the outliers is causing the mean to increase, but the median is staying about the same. However, if I add enough outliers, eventually the median, did you notice the median just shifted just a little bit because now the middle number is different than what it used to be. So if I continue, you can see that there will be some slight change in the median if I keep adding points, but not nearly as much as the mean. So it's resistant, but doesn't mean totally immovable. So if you're describing that, you might say the mean it either doesn't change or only changes very slightly with an outlier or a group of outliers added. The next characteristic I want to look at is that the median acts, or the mean acts as a balancing point of a histogram. So if this is a histogram, and you can picture this this red line balanced on this little fulcrum here, the mean balances the histogram, whereas the median divides its area in half. So what would happen if I move some of the blocks? So if I have this situation and I move some of these blocks over here, and so now it looks more like this. I don't know if this matches what you have here, but just for an example, notice that half the blocks are still on one side of the median and half on the other on the blue line. So the median hasn't changed, but now we would recognize that this fulcrum would no longer be in the right place. This red line is going to tip that way unless I move the mean over a little bit to balance it out. So just to summarize here, using the little diagram I have here, the median is still in the same place because this is still half of the area and this is still half of the area. So the median didn't change. But the mean changes because the balancing point has to change. Now we can look at this as an example with some data from the Colts players. So this graph shows the Colts players' average annual salary in 2016. So this is recent data I just got off the internet. Of course, this is if you're hearing this video in 2016. If you aren't, then it's not recent anymore. So I want you to notice here's the mean. So the average annual salary of all of the 83 Colts players that are in this list is about $2 million per year. The standard deviation, which is a measurement of variation, is 3,500,000, so it shows that we have a lot of variability in their salaries. This group of numbers is known as the 5-number summary, and this shows the median salary. So here's the median salary. Notice the median salary is $710,000, considerably less than the mean. We have the minimum salary here, the maximum salary, and then Q1 is halfway between the minimum and the maximum. So basically we'd say the lower fourth of the salaries are between $450,000 and $450,000 and $540,000. A fourth of the players, the lowest 25%, have salaries in that range. The next 25% have salaries between $540,000 and $710,000, and so forth. Maximum salary, $24,594,000 per year. Andrew Luck. That is Andrew Luck right there. Hopefully he will earn his keep. Now, if I mark the mean and the median on this graph, the median is to the left and the mean is to the right. So when we have a skewed right graph, the mean moves to the right. Okay, so that's what we see here. The mean moves to the right of the median. If it was symmetric, they'd be in the same place. Now, which measure of center is the best for describing the typical average salary of a Colts player? Not starting salary, but their average yearly salary at this point in their career. Rule of thumb here is that if the distribution is skewed or has outliers, use the median instead of the mean. And the reason why is if we look at the salaries, the median actually describes the majority of the players much better than the mean does. Notice here there's 83 players in the sample, and this one bar has about 45 of the players in it, and then if you add this bar, it's another 55. So maybe about 2/3 of the players are in this region here. So the median represents the majority of the players much better than the mean does. One more interesting thing about the median and the mean is how are they related to each other and the shape of the distribution. So here I've calculated the median, and here's an example where the median is not the middle number because there are an even number of data values. There's 12 data values here, so we have to average the two middle numbers to find the median. If you add up all these numbers and divide by 12, you get 3.5. So here the median and the mean are equal to each other. Now let's make a dot plot of this data, and we see there's 2 1s, 3 2s, a 3, a 4, 3 5s, and 2 6s. So notice what we have is a very symmetric distribution. It's bimodal and symmetric. So here's a true statement. If the distribution is symmetric, the mean is approximately equal to the median. Now in this case it's exactly equal because it's exactly symmetric, but realize most of the distributions you're going to encounter are not going to be perfectly symmetric. So if it's fairly symmetric, then we would expect the mean and the median to be approximately equal. Okay, looking at the next one here, we have 10 data values here, and once again an even number, so we average the middle two numbers to get a median of 2.5, but when we calculate the mean, it turns out to be 3.2. So let's look at this dot plot. We have 3 1s, 2 2s, a 3, 4, 5, 6, and 7. So we have a skewed right distribution here. Notice it's skewing to the right. So here we notice that if we have a skewed right distribution, the mean is greater than the median. And by the way, if it were skewed left, my handwriting is not terribly good, the mean would be less than the median. Now let's take a look at this last one. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data values. If you calculate the median, you get 3.5. If you add them all up and divide by 12, you get 3.5. So the question is, what does this tell us about the data? Now you see this be careful here, so you're probably realizing something's probably not right, because my guess is the data would be symmetric, but if we actually plot these dot plots, they are not symmetric at all. So here is the takeaway from this. If the median is approximately equal to the mean, we can't say that the distribution is necessarily symmetric. The converse is true. It is true that if the median and the mean, if the distribution is symmetric, I know that the mean is approximately equal to the median, but the converse, saying it the opposite way around, is not necessarily true. So I just want you to be careful about that. Don't assume that the distribution is symmetric if the median and the mean seem to be about the same.